to the complaint made yesterday by the Greek.
I'm talking with Richard Heyser, who is a senior editor of Audio Magazine and describes himself as an audio hobbyist who let the hobby get out of hand. And he's been doing audio on and off over a period of more than 20 years, I gather.
That's right.
And some of you who read Audio Magazine may know him as the author for the past, about 2 years or so, of the exceedingly detailed and highly technical loudspeaker reviews in the magazine, and the author also of a number of articles on audio generally, but particularly audio technology, physics, mathematics, what have you, as it applies to speakers. And I made contact with, may I call you Dick?
Yes, please do.
A few days ago, and decided it would be really worthwhile to interview him on what is to me one of the most fascinating topics in audio, the whole general topic of how does what we measure correlate with what we hear, or does it at all? And it turns out that that's just about his favorite topic too.
Well, let me repeat what I said to you a little bit earlier about how I got into this business, because it is a hobby.
Mm-hmm.
And the obvious question is, if it's a hobby, then you're in it awfully deep. And how come you're involved in the esoteric applications of mathematics and so on to audio? And the answer is that in the earlier involvement was in the broadcast end, was doing remote broadcasting for the university when I was going to University of Arizona. Actually, prior to that, had been involved in listening and wanted to design and build better vacuum tube systems, which I did. During college years, of course, you really didn't have much opportunity to do anything but listen. You couldn't play much with design. But after I graduated, I could then, first of all, I got a job so I could begin buying things, which were only dreams before, and really began seriously considering how to make it better. And very quickly discovered something that was known to virtually everybody that had been in the business, and that was that I could hear things which clearly didn't seem to show in the measurements I was making. I'm talking now about distortion. And when I began inquiring about this with professionals, I found, yes, indeed, they could hear the same sorts of things. So that began a long trek upward of what in the devil am I hearing and others are hearing that doesn't seem to show in the measurements, and can we measure it? And conversely, why are some of our measurements so grossly insufficient in characterizing what we hear? And in the process of experimenting, I found that I could readily determine, as could many, many other people, fractional percentage distortion in amplifiers while listening through loudspeakers that had many orders of magnitude more distortion than that. And so I wanted to measure the loudspeaker. After all, I was interested in amplifiers, but if you're going to listen through speakers, you'd like to know what is it that you're hearing in the amplifier that doesn't seem to be evident in the loudspeaker. And I needed an anechoic chamber. Well, even a dedicated hobbyist sort of stopped at $250,000, which is about the going price for an anechoic chamber at that time. Much, much more expensive now. So I turned to the only field I had, which was electrical signal processing, and came up with a method of measuring a loudspeaker while it was in a room and measuring the anechoic properties of it. And that led very quickly to a host of revelations, some of which were known to others, revelations to me, others which were not known to others who had been experimenters in the field, and it exploded from that point on, and is still in the process of a nova-like expansion. One of the very first things that came out was that while I did not have an anechoic chamber, I did have a method of measuring the property that, mathematically speaking, was the anechoic chamber response.
Perhaps I should just interrupt for a moment to explain to some of our less technical listeners that an anechoic chamber is a chamber that has essentially zero reflectivity or zero reflections off its walls. It's constructed in such a way that everything that impinges on the boundaries of the room is absorbed and it facilitates certain kinds of measurements.
Right. It's the so-called free field test or
It's
anechoic test.
as though you had whatever sound source you're measuring out in the middle of an open space, suspended in midair with no reflecting objects anywhere around for yards or miles or whatever.
Right.
Okay.
Well, the equations which came out of the analysis that proved that yes, I was measuring the anechoic property, and that was subsequently verified by actually going into chambers and comparing measurements, said that there was another part of the measurement that was in the equipment, the electronic equipment, that really had not been looked at in previous acoustic measurements made on loudspeakers. Now we're talking about 40 years of loudspeaker experience. And that property was the phase. For 40 years, it had been assumed that what one meant by the frequency response of a loudspeaker was how much sound is a function of frequency or pitch. But phase, it turned out, was also important. As a matter of fact, phase was in many respects just as important as how much. But phase had not been measured in an anechoic chamber before, at least not to my knowledge. And I began digging back and talking to people who'd done this work, and I found no, they hadn't done it.
Mm-hmm.
And as a matter of fact, phase was such an interesting subject. People would say, phase, what's that? So
well, I'm wondering if we should make another little interruption to explain to our listeners exactly what phase is.
Well, phase is, if you wanted an oversimplification, is a manifestation of when the sound gets to you. Mm-hmm. A sound not only has a how much, but it has a when. And while the early experimenters and those today who have anechoic chambers were in fact measuring the how much of sound, the when really was of no concern. Mm-hmm. Whether the microphone was 1 meter away from the loudspeaker or 3 meters away was immaterial to their measurement. Mm-hmm. But it made one heck of a lot of difference, actually, in the performance if you measured it properly. And when I began making the measurement of phase on loudspeakers, then the second revelation occurred when I found that many loudspeakers had significant parts of their frequency spectrum that were, now this is going to really be techno-freakish, non-minimum phase. Now let me say simply that for at least 40 years, engineers and people in the technical end of things had made the assumption that if you flattened the frequency response, it was obviously better. Mm-hmm. If you made an amplifier that had plus and minus no dB variation over a full frequency range, it clearly was a better amplifier than one that had a response that was plus minus 5 dB, let's say, which some of the very early amplifiers were. However, and it was generally assumed that if you wanted a better loudspeaker, that it should have a flatter response. Mm-hmm. Now, the people who really were into it, the designers of speakers, were well aware of the fact that if you took a good sounding loudspeaker, one that people liked the sound of, that sold well, was considered accurate, and measured it in an anechoic chamber in the traditional way, you quite frequently found the response would look more like an alpine skyline in response than the flat line you'd like to have. And about every 5 years, some engineer would decide, oh, well, I can make this a better sounding loudspeaker. So he would measure in the chamber and find frequencies where the sound was high, frequencies where the pressure was low, and he would fill in the dips and chop off the peaks, ending up with a flatter measuring loudspeaker. And the moment of truth would come when they would take this loudspeaker and the production version of the same thing that hadn't had this wonderful treatment, and they would let people listen to it. And inevitably, the response was yuck. Mm-hmm. You know, it measured
the response
better,
of the listeners was yuck.
The response of the listener was, it doesn't sound as good. And this was also observed in certain cases in disc cutters. But it was one of those problems that they didn't worry about.
When would you say was the earliest occasion when some audio technical person proposed that it might have to do with phase irregularities rather than frequency irregularities?
September 1969.
No, that's a pretty specific date.
Yeah. It's a paper that I gave, and the reason it turned out that the flattening of the response didn't always make it better was that you were only flattening one part of the measured property, the amplitude, the pressure, the how much. The phase, on the other hand, if you flatten it using conventional circuits, that is, flatten the amplitude, you may just have fouled up the phase.
Mm-hmm.
And if you were flattening the response of a speaker, which was of the type that's called non-minimum phase, and we can go into that a little later, you just would end up with a loudspeaker that measured flatter in amplitude, measured very irregular in phase, and sounded terrible relative to its original state, assuming that it were a speaker that had been designed by people who knew what to listen for, and they experimented and got a sound that they wanted. So phase turned out to be a very important thing, but it was a technical stumbling block, because here was 40 years of experience down the tubes, you might say.
Let me backtrack for a moment and explain a little bit with your assistance, if I can, the importance of the thing, of this business about phase. I think probably most of you are aware that musical tones actually consist not just of one frequency alone, but of a whole cluster of frequencies for every note that you hear. Usually there's one that's lowest in frequency, which is called the fundamental, and that's usually principally responsible for the pitch, the subjective sensation of pitch. But then the phenomenon, the physical phenomenon that gives the sound a distinctive character is a whole train of overtones or harmonics that go along with the fundamental. And each instrument, each sound source, in fact, has its own distinctive arrangement of harmonics, which are integral multiples of the fundamental frequency, 2 times, 3 times, 4 times, 10 times, whatever, of the fundamental. And not all of them may be present, and they're almost certain to be present at different amplitudes. It also happens, at least this is my understanding, that they don't all start at the same time, and that it's quite possible that, for example, a couple of harmonics may precede the fundamental, or vice versa, depending on the nature of the instrument. In fact, there are stories of an interesting little demonstration that was done by somebody of recording a bunch of familiar musical instruments and then on tape, and then cutting off the first couple of inches of tape and making a loop out of the remainder, playing the thing around and around and around, and most people couldn't tell what the instrument was. That's because right. That very characteristic attack sound, let's say the bite of the bow into the string, or the initial lip and mouthpiece sound of a trumpet, or the initial cracking of a reed or whatever, was missing, and so that the ear lost some of its cues. Now, it's of no real consequence that all the harmonics don't start at the same time, as long as that time relationship is preserved throughout the whole processing chain, from microphone through tape recording, FM broadcasting, limiting, compressing, whatever you do, till it ultimately reaches your ears. And what is beginning to be discovered, and in a way seems obvious, if you tinker with that, if you tamper with that time relationship, the sound will in some way be less than natural.
That's
Does
correct.
That seem
That's
like
absolutely
a
correct,
decent summary of what's going on? And phase is just a somewhat specialized way of referring to time delay. Instead of referring to time in terms of seconds or minutes, or time as indicated around the face of a clock, we can talk about events in terms of when they take place in a cycle of vibration or oscillation. If you're familiar with the notion of a sine wave, which starts at 0 and rises to some positive value and declines again to 0, and then goes to a negative value and returns to 0, that defines a complete cycle. And that cycle takes a certain amount of time, which is to say there are so and so many cycles per second, which is the frequency. And you can speak of things being, how shall I put it, in a phase relation, which is a time relation, beginning somewhere else in the cycle.
Right. May I give you, to me, a good
help.
Example? All right. We're looking right now at the old clock on the wall. That consists of 3 rotating vectors, if you will. It is a fundamental, a 12th harmonic, and a 720th harmonic, which we call an hour hand, a minute hand, and a second hand. Now, by convention, 12 o'clock position is when all three harmonics, or the fundamental and those particular two harmonics, have a particular phase relationship. That is to say, they all get to the same point starting at the 12 o'clock position at precisely a given moment, which is midnight.
Uh-huh.
And that, frankly, is how one is able to tell time by, even if the numbers on the clock are deleted, because we know the phase relationship in the fundamental, the 12th harmonic,
the
and the
positional rotational relationship of the hands is what serves as our clue.
And if one were to be a deranged clockmaker and to shift the phase of the 12th harmonic relative to the fundamental, he would not have the same sequence that he has by convention now. Let's say that at midnight you took the minute hand, keeping the hour and second hand where it was supposed to be, and you cranked the minute hand to the 5 o'clock position.
Uh-huh.
It's wrong now.
Uh-huh.
Because every hour the minute hand would be at the 5 position.
Right.
Well, that's not the proper phase relationship of that 12th harmonic relative to the fundamental.
Right.
So that, to me, is a visual example of a relationship of a very complicated structure that's a repeating constant rotational rate. Now, that's super slow, but if you're talking about concert pitch A of 440 revolutions per second, you remember we used to call them cycles per second, you can have a 12th harmonic. You, of course, have second harmonic, third harmonic, and so on. So you have a much more complicated thing. But the relationship of the harmonics and the fundamentals, and the fundamental, is a very distinctive one for each instrument. And if you mess around with that, in some measure, you are creating a distortion. Now, whether that's audible depends upon a great many other considerations, but clearly it is not accurate.
Okay, that helps. That's a very nice analogy. Where were we before I so rudely interrupted you to talk about phase? You were on your way to some.
Well, phase is probably to me, was the stepping stone that took me to what I think is a more accurate path to begin answering the question that I really started out on, and that was, why can't I seem to measure what I hear? Because the moment that this phase showed up, and I didn't invent phase, good heavens no, it was around a long time. I simply call people's attention to it in a particular type of measurement. And in trying to interpret what this phase meant, well, the phase is not really time delay, but it's the strongest manifestation of time delay you can have in a system if you have nothing else that you can play with. And it said basically, well, time is a partner. Well, clearly time is a partner. Try to write a musical score without involving time. And when you now begin looking at the mathematical relationships that are involved in this, you are now off into involving oneself seriously with time. And then the next immediate step was, well, for heaven's sake, if you have a mid-range driver and a tweeter and a loudspeaker system, and the sound from them doesn't arrive at your ear from the same path length, then there's a time difference. And maybe the mid-range is carrying the fundamental and the tweeter may be carrying a higher order partial. So now you have fouled up the time alignment of the loudspeaker. What has it done to the sound? Let me start out with something that may be a shock to people. It's perfectly evident. I point out to my friends in the audio engineering profession, I say, really, an audio engineer shares the professional goal of a magician, because you're both trying to create an illusion in the mind of the listener. And in case of audio, it's the illusion of sonic presence. If you set up, let's say, 2-channel stereo system and measure what's in the listening room, it does not measure in accordance with what you hear. You may hear the sound of a string section coming from left of centers, let's say, and behind the wall. There's no string section there. There's no virtual source of sound coming from there. You have, through experience, melded the two disparate sources, which are the left speaker and the right speaker, into the illusion of sonic presence. Now, how in the devil do you handle that? Because clearly now you have two situations which might give identical subjective effects. If you heard the sound of a single instrument, that seemed to be coming from position in space, if it in fact was coming from two or more positions in space and were combined in your mind to create the illusion of an instrument, the measuring microphone does not have the same illusion. So conceivably, there are two situations which would measure differently. Suppose you try to describe the sound of an instrument to somebody else. In order to describe that sound, the sound has a where. It may be to the left of center and back a certain distance and up a certain angle. It has a when. It has a tone or property of tone. It has an intensity. And those are independent properties. When an instrument is playing and what it is playing and where it is playing from are really not dependent properties. You may have an oboe in a position, you may have a stringed instrument at the same position. That is, as far as the mathematical description, really a multidimensional expression. And yet, when we measure an amplifier, let's say the amplifier that fed the loudspeakers that gave that illusion, we measured volts as a function of time.
Mm-hmm.
We made a one-dimensional measurement. Now, in that volts as a function of time is where, when, tone, how much. And if you have two channels, the relationship between the two channels and the absolute values of each channel, in fact, go to make that up.
It's a kind of encoding.
It is, in fact, an encoding.
Mm-hmm.
So that what occurred to me with almost a shock, and this was a good 6-7 years ago, was, my gosh, we are not measuring what we're listening to. We are making a one-dimensional measurement. We really want to try to interpret that in a multidimensional mode. It makes no sense to, say, put a sine wave into an amplifier, see how that sine wave is distorted, and try to relate that one-to-one to subjective distortion until we can relate it to the way we describe sound. The fact that you may have, say, 1% harmonic distortion may interact, depending upon the type of distortion, in a different way. For example, you may have a situation where the thing that gave rise to the harmonic distortion you measured caused a lateral smearing of the instruments. That would be one type. Another type that would give you the same number for harmonic distortion, but of course having subtle differences, would simply have given you a change in the tonal property, the timbre, without a change in space. Now you see a brand new ball game is being opened.
Yeah, but it's a little vague in my head, and I wonder if you could somehow go back over that and explain it, or
Yes.
give me some examples. Well, the lateral smearing thing is what really interests me, because I recently had the experience, finally, of discovering what people mean when they talk about depth and localization in a stereo image, specifically with regard to cartridges. I was sitting with a friend, and we were swapping cartridges and playing the same bit of a record over and over again, and everything else being presumably equal, or as close to equal as we could do it, in a home kind of situation. And there was no question that certain pickup cartridges gave a more defined and focused spatial illusion than others.
Mm-hmm. Mm-hmm.
This is completely independent of, let's say, brightness or tracking qualities or anything else. There was an actual spatiality. I cannot guess what is responsible right now for the image of depth, the notion of a third dimension that's perpendicular to the plane between the two speakers. Maybe you could illuminate that a little bit.
What is distortion is an interesting question that is not at all easy to answer. Let me define distortion in a very strange way. Let me say that if you have a subjective illusion, that there is associated with that illusion a geometric configuration. It has a where, a when, intensity, and so on. And these are independent attributes. And let me define, just for the sake of this discussion, distortion as a change in the type of geometry. Now, mathematically, what happens when you do that? You find that your previously separated coordinates, like where and what tone, now become slightly cross-coupled. You get into what's called a curved geometry. You find that there is now an interaction between where an object is and what tone is being played. So that if you have such a distortion defined in the geometric sense, you can in fact have a lateral smearing of instruments that's a function of pitch. Now, a loudspeaker does that. The polar pattern, in fact, does that on you. The effect of distortion, in that case, in an imperfection of the left-rightness of a loudspeaker, let's say, of uniformity for pitch, is in fact to create a lateral change of the instrument's position. It's a cross-coupling of what was formerly
Three
independent properties. Now you find that they are no longer truly independent, but where is a function of tone?
Let me test my understanding of that, if I may. For example, dealing with a single musical instrument, which is producing musical notes which have fundamentals and harmonics and so on. It seems to me one example of how this might work is if you had, if the fundamental were being handled by the woofer and some of the harmonics by the mid-range unit or something like that. And they had, well, the most obvious thing is that they are obviously physically in different places on the loudspeaker baffle board. So there already, the instrument would be being stretched out of shape to some extent by the fact that these things were now being radiated from different points in space. But I think, if I understand what you're getting at, that even with a single driver, let's say just a mid-range unit, whose directivity characteristics or dispersion pattern or whatever you want to call it, polar pattern, is not the same everywhere, that isn't completely uniform, that depending on where you stand, different frequencies will be, will seem to be imaged in different locations.
That's right. If you were to move around the listening area, you would find that the stereo illusion, for example, may shimmy and wander around behind the speakers with you in a manner that would be different from one loudspeaker to the next.
Well, now, does that have any relationship? I've noticed, for instance, that well, let me give this example. If you're listening to a mono signal and you're exactly centered between the speakers, or let's say on there you arrange an equilateral triangle with the speakers at 2 points and you at the remaining point or something of that sort, you hear the signal, of course, classically as coming directly from some point in space between the two speakers. If you now move to the right or left, the image moves with you.
That's correct.
Now, if you do that with a stereo image, whether or not the image moves with you and to what extent seems to depend on a great number of variables, and it is different with different speakers.
It is different, that's right.
Now, is this related
It is
to that?
indeed,
Okay.
yes.
I don't quite understand how yet, but it just intuitively seemed to be.
When I said yes and no in answer to your question, now we're getting to some of the reasons for yes and no, and that is that if you begin defining the geometry in these terms, and distortion in terms of geometry, you find that you have a very powerful tool, and if you begin digging into reasons behind these, you in fact find that there are good ways of looking at this. The most important thing that comes out are predictions of what to measure and what it should listen as. And several of these have, in fact, come out of the math and do indeed work. The interpretation is a very, very complicated thing. You cannot say, and let me just make this as a flat statement, you cannot say that 1% distortion is going to sound dirtier than 0.1% distortion. Flat out. Because you're talking apples and oranges. When I said 1%, I did not specify everything about that device, any more than if I'd said that a plus minus 1 dB frequency response speaker must sound cleaner than a plus minus 5 dB speaker. And I would be in error for exactly the same reason. You must measure not only the amplitude of the harmonic distortion, but its phase. If you imagine a device in which, as the signal gets louder, it creates harmonic distortion in the conventional sense, that is, harmonics begin coming up, which shouldn't be there. If you were to put a pure pitch tonal, you may get a second harmonic, a third harmonic. But the phase of them may be a function of level. The timbre of the sound for an instrument that now has harmonics will change with sound level.
So that the string bass, let's say, that's being bowed as it gets louder, its timbre may change in a way that has no relationship to the way the timbre of the actual instrument would change.
Yes.
Okay.
And it can get exceedingly complicated, and one cannot just make a gross statement that A is going to be better than B. You have to now take very complete measurements of these things.
Now, is it not also important to know which harmonics are present
Absolutely.
and in what relation?
No, I
It's
cannot,
not just phase or amplitude of,
right.
of the sum total of them, right? But you have to know which ones are there.
Yes.
Okay, fine.
I must also point out that those of us who are technical people are guilty of a terrible error. We use linear mathematics to explain nonlinear phenomenon. The concept of harmonic distortion, for example, is based upon what's called a Fourier series expansion, which is really a linear expansion. In a general nonlinear sense, you may have subharmonics that you don't run into in a normal Fourier expansion. Loudspeakers create subharmonics.
I wondered about that.
Very definitely I do. And you can, and in fact, have integral harmonic ratios in mixed tones, for example.
That I know about.
So that simply making a sine wave measurement may be very misleading. Particularly if you take a one-number measurement. You say take the total sum of the mess that's left after you subtract out the fundamental. If you have no measurement at all, this measurement is better than nothing. But that's about all it's good for.
It's simply too gross, right?
It is
not
too
fine enough.
gross.
Its
That is
resolution isn't
precisely
fine enough. It
correct.
doesn't tell you enough.
And we tend to use the linear concepts for that. We tend to equate, for example, a given harmonic distortion to accuracy without recognizing that there may be other partials in there that are very distressing to the ear that may or may not be harmonically related. Magnetic tape distortion has a very high percentage of harmonic distortion.
That's something I'd like to get into. And so we shall next Friday at 9 p.m., when again, as tonight, my recorded guest will be Richard Heyser, senior editor of Audio Magazine and one of the most serious audio hobbyists I've ever met.